Hello everyone, and welcome to today's lecture, which is lecture 3 of Galaxies at Stockholm University. This lecture is a two-parter, which comes in 3 parts. The first part is called Electromagnetic Radiation from Galaxies, and this one is split up in 2 videos. One about the spectral energy distribution and one about galaxy spectra. And the second part is about the statistical distribution of observed properties such as mass, luminosity, and color. And this one will take up the last video. As we can see here, the first video will be about the spectral energy distribution. The second one will be about galaxy spectra. And the third one will be about the statistical distributions of color, mass, and luminosity, with a certain emphasis on the color bimodality and the star-forming main sequence. But first, let's dive into the spectral energy distributions of galaxies and the effects of dust extinction and dust emission. How the emitted radiation from galaxies is distributed over wavelength contains a lot of information about what is going on inside said galaxies. We call this the spectral energy distribution, and it shows the overall shape of how the emission varies with wavelength. So in a sense, one can see this as a very, very coarse-grained spectrum. It doesn't contain any of the smaller details, but just shows the overall shape. So different physical processes and astrophysical sources dominate at different wavelength ranges. And if we kind of simplify things a lot, we can divide them into the 3 main components, which are stars and stellar remnants as the first component, stellar remnants including, for example, supernovae, planetary nebulae, white dwarfs, and so on. And the second main component is diffuse matter, as we call it. That means ionized and neutral gas in the interstellar medium and the circumgalactic medium. The interstellar medium being the denser medium inside the galaxy between the stars, hence its name, and the circumgalactic medium meaning the somewhat more diffuse gas that is surrounding the galaxy and its stellar population. And finally, the third main component are dust grains. These emit gray body radiation after being heated by stellar emission, as I touched on in the last lecture. And they also absorb at other wavelength ranges, because that is what heats them, and they re-emit this absorbed radiation in the infrared, as we will see in a little bit. So this figure shows us like a typical spectral energy distribution and a typical low resolution spectrum of a galaxy or of various galaxies. As we can see, the darker spectrum here shows early type galaxies, and the medium one here shows moderately, not too strongly star-forming galaxies. And finally, the lightest one shows irregular galaxies, which are often much more strongly star-forming than the more quiescent spiral galaxies. But so you can see that these have quite different overall shapes. But they also share this like double peaked distribution if you squint and look at like the big lines here. What you see in these points with arrow bars are typical measurements as you would see them in photometry. That means if you would measure their emission inside a broad photometric filter using a camera, an imaging camera rather than a spectrograph. where what you see in the lines here is what you would see if you were observing the galaxy with a spectrograph. The photometric filters used are shown down here, where you can see their transmission coefficient as a function of wavelength. I can tell straight away that the filters we see here look like, no, actually I cannot see exactly which filters they are, but they are quite typical filters to use in these wavelength ranges. Stars and stellar remnants are dominating emission in the ultraviolet, the optical, and the near-infrared wavelength ranges. This mainly comes from photospheric blackbody radiation, and that's basically what we see when we look up on the sky and see the sun is shining. That's the kind of light that dominates in this part of the electromagnetic spectrum from a galaxy. Overlaid on this, as we have seen in previous lectures, are also stellar absorption lines, that is, absorption lines from various elements in the photospheres or in the atmospheres of these stars that emit this radiation. There are also circumstellar dust shells which absorb some of this light here, and re-emits it in the mid to far infrared wavelengths out here. We will get back to that below. And finally, there are accretion processes from, for example, binary stars and pulsars. These are very, very high energy processes, so they mainly emit their radiation in X-rays and gamma rays, which is far outside the boundaries of the wavelength range of this figure, so way out here to the left. The second main contributor to the spectral energy distribution of a galaxy is the diffuse matter, the ionized and neutral gas. One very important component of this is the emission from atomic hydrogen. So that's neutral hydrogen, but not molecular hydrogen. Neutral hydrogen emits line emission with a wavelength of 21 centimeters. Thinking about that, by the way, that is a very long wavelength compared to the far ultraviolet or the X-rays or gamma rays that we see with some of the other processes. So this is very low energy processes, but there's a lot of neutral hydrogen in the universe, so we can still see sometimes quite strong radiation in this 21 centimeter line. On top of that, we have vibrational and rotational emission lines from cold molecular gas. These line complexes are, well, complex. There are so many different modes and like vibrational and rotational modes in these molecules that even relatively simple molecules can give rise to a large number of emission lines. But those emission lines are often not particularly strong. They are observable, but they are not super bright. These are usually found in the mid-infrared and to the millimeter range, so basically roughly the block that we have drawn here. There's also, as I mentioned earlier on in the last lecture, nebular line emission from ionized gas that comes from the diffuse medium. This is mainly found in the far ultraviolet, the near ultraviolet, the optical, and the near infrared wavelength ranges. So all these ranges, which I otherwise said were dominated by stellar continuum emission from the stellar blackbody emission. But on top of this stellar blackbody emission, we can also have some quite strong, narrow emission lines from the ionized gas. And as we shall see later on, these can actually be, by comparison, very, very strong even. And finally, also here we have very high energy processes, very hot gas shocked or in early type galaxy halos, which emits light in X-rays and gamma rays. So again, way outside the range of this figure. And finally, as the third major component of the interstellar medium, we have emission from dust. So as I've touched on earlier, dust will absorb light in the UV and optical, so over here. And this absorption will, of course, lead to the dust grains being heated up. And this, in turn, leads to them emitting that excess energy as thermal radiation. And thermal radiation at the temperature of these dust grains has a very long peak wavelength, if we remember the Wien's law. And that means that even though it might be light absorbed in the ultraviolet and optical, it is re-emitted in mid-infrared, some near-infrared, mainly mid-infrared, and all the way out in the far infrared wavelength range again. Different dust grain sizes and materials emit at different wavelengths. So that means that the shape, the spectral shape of the dust emission can tell us something about the grain size distribution in the gas that we're studying, as well as the chemical composition of this dust. And finally, we can have quite strong emission from what is called polycyclic aromatic hydrocarbons, which are, well, simple is a relative term here, but they're simple organic molecules. But that's just because organic molecules can be extremely complex. These molecules are still quite complex compared to most other molecules we will find in astrophysical clouds. But polycyclic aromatic hydrocarbons, or PAHs, or sometimes just PAHs, are very important both for the emission spectra that we see from these galaxy regions, and also it is believed that they are ultimately the molecules that will later on compound and form the fundamental building blocks of life. These are emitting mainly in the mid-infrared spectral bands. You can see some of them here. These are not individual single emission lines. These are complex compounds of a large number of emission lines that form these combined shapes, as you can see them here. Some general considerations. Overall, as you can see, a typical galaxy, and that is across the range of galaxies, the galaxy types that we see in the figure here, we still see that typically they are double peaked in shape, peaking in the optical and in the far infrared. But the relative strengths of these peaks vary with various different things, such as stellar population, dust content, star formation activity, star formation history, and so on. Which also means that we can work the opposite way backwards and look at this, this relative strength of the peaks and the overall spectral energy distribution, and learn a lot about all these different properties of a galaxy. Finally, the UV and optical emission can be strongly affected by dust extinction, which is, well, it says strongest in the mid-infrared spectral bands. That is not true. I'm sorry. That is the re-emission of this dust extinction. But yes, dust extinction can have a very strong influence on the shape of the spectral energy distribution and the full-on spectrum of a galaxy, especially in this region here. And now we're going to take a closer look at how that looks. So absorption by dust grains it affects various wavelength ranges very differently. And that is because of this quantum mechanical effect that if the wavelength of a photon is much smaller than the physical size of an object, then it is almost certain to be absorbed by it. On the other hand, if the wavelength is longer than the size of the object, then it will not be absorbed. It will pass right through it or right past it without being affected by it. And then there is a kind of in-between region where the absorption probability will vary strongly with exactly how similar the dust grain size and the wavelength are. So that also means that we, as I said before, when we see the distribution of how much light is absorbed at various wavelengths, will also give us a knowledge of the typical distribution of dust grain sizes in the cloud that is doing the absorption. That's quite useful. If we look at a mathematical description of absorption by dust grains, we can see that it can be described as the initial flux, as we see it here, times an absorption profile, which we see here, or like a transmission function. And this transmission function is in turn given as this functional form, where we see that it is this number here times this function here, which is important, which we basically call the extinction function or the attenuation function, plus the color excess that you will remember from the last lecture, which is how much the colors of how much the colors of B and V in the B and V bands are deviating from what we would expect if there were no dust. And this in turn can be rewritten as, so these two here can together be rewritten as what we call the absorption function. So this, as I said, K is known as the extinction curve, or in some cases the attenuation curve. And again, it depends on the dust composition in grain size distribution. Oh, I just realized you couldn't see the last part here. The function K lambda is known as the extinction curve, or in some cases the attenuation curve, and it depends on the distribution of grain sizes, which in turn, in part, depends on the chemical distribution of the dust, plus the physical properties in the galaxy where the dust grains have formed. That was it for the first video. I will see you in the next one, and thank you for staying with me so far.